everyone, today we're thrilled to present our research project about integrating geodetic engineering principles with programming techniques to enhance geospatial analysis together with my developer Mark Adrian Flores. Our project delves into the fascinating realm of combination traditional geodetic knowledge with modern computational methods to solve complex spatial problems and improve data processing efficiency.
Geodetic engineering involves measuring and understanding the Earth's shape, space orientation, and gravity field. And by integrating programming techniques, we can apply algorithms and automation to some tasks, such as to calculate distances between cities based solely on their coordinates. For example, using the Haversine formula, we can accurately compute distances between cities despite their locations, and this paves the way for more effective route planning, navigation systems, and GIS.
Methodology involves the development of custom algorithms tailored for geodetic computations. One key function, calculate distance, takes latitude and longitude, coordinates at inputs and returns the distance between 2 points. This function employs trigonometric calculations and Earth's radius to convert angular distances to linear distances, ensuring accuracy in geospatial measurements. In addition, we utilize libraries like NumPy for numerical computations and pandas for data manipulation, enhancing our project's capabilities in handling large geospatial datasets.
Our project's objectives encompass several key areas. Number 1, developing a deeper understanding of geodetic concepts and programming languages, bridging the gap between the old surveying methods and the modern data processing techniques. Number 2, designing and implementing algorithms that automate geospatial data collection, processing, and analysis that leads to more efficient and more accurate results. Number 3, integrating geodetic coordinate systems and spatial reference frameworks into programming frameworks, and this ensures seamless geospatial data handling across different platforms and applications. And lastly, number 4 is by creating geodetic software tools that leverage programming functions to enhance accuracy, efficiency, and reliability in mapping and measurements.
This part imports the NumPy library, which is used for numerical computations in Python. Here, a dictionary named cities is created to store sample geodetic data for cities. Each city is a key in the dictionary, and its value is a tuple containing its latitude and longitude coordinates. This defines the calculate the distance function, which takes two coordinates tuples, coord1 and coord2, as inputs and calculates the distance between them using the Haversine formula.
And fourth, this defines the calculate the distance function, which takes two coordinate tuples, coord1 and coord2 as inputs and calculates the distance between them using the Haversine formula. And this formula actually calculates the distance between 2 points on the surface of a sphere, in this case the Earth, given their coordinates. Fifth, this part solves for the distance between all pairs of cities in the dictionary by using a nested loop. It iterates over each pair of cities. It checks if they are different to avoid solving the distance from one city itself. And then it calls the calculate distance function to compute the distance between them. And finally, the distances are stored in the dictionary with keys that acts as the route between cities.
Section prints the calculated distances between cities. It iterates over the items in the distances dictionary and prints its route along with its corresponding distance in kilometers, formatted to do decimal places. The results show the distances between various city pairs in kilometers calculated using the Haversine formula based on their geographic coordinates. Each route's distances provide insight into geographic spread and relative proximity of the cities. For example, longer distances like New York City to Los Angeles highlight significant travel distances, while shorter distances like New York City to Chicago reflect closer locations within the same country.
The outer loop iterates over each city, city 1, in the cities dictionary. For each pair of cities, city 1 and city 2, the code checks if they are different to avoid solving the distance from city to itself. If these are different, the calculate distance function is called with the coordinates of the two cities to solve for the distance between them. The distance is then stored in the distance dictionary with a key that represents the route. For example, NYC to Los Angeles. For our project, we demonstrated the application of programming in geodetic engineering, and our algorithms can calculate distances between cities, and this showcased the power of automation and computation in geospatial analysis.
Geodetic engineering principles with programming techniques is not just a technological advancement, but a paradigm shift in how we approach spatial data, analysis, and geospatial applications. It empowers us to solve complex problems with precision and efficiency, opening doors to new possibilities in mapping, navigation, and environmental modeling.